All right, today we'll get started into actual calculus stuff. And we talked about how there are two big ideas in calculus. One of them we're going to start talking about today. But it turns out that both of the big ideas of calculus involve the idea of limits, which seems odd at first. But the first one is actually, you'll see it fairly quickly. The second one, when we get to it, it'll be like, oh yeah, that is a limit. But you wouldn't think of it immediately. At least I wouldn't have. This part, I was like, okay, yeah, that makes sense that that's a limit. The other one, it took me a while, and I was like, oh yeah. All right, so we talked a little bit about this yesterday also, the average speed of a moving body during an interval of time. You find that by dividing the distance covered by the elapsed time. We talked about that with the dropping ball, right? And all of you understood that, sort of almost at an intuitive level at this point. All right. So the formula for that, or for the average rate of change, this average rate of change formula is going to come up over and over and over and over again. On a time interval from t to, that's a t plus h. I know it looks like tth almost, but right here this is t plus h, is given by this formula. The average rate of change is the change in the function over the change in time. So the change of the function is f of t plus h minus t plus h, minus f of t over t plus h minus t. Okay, it's the change in the output over the change in the input. Now, back up for just a second. The change in the input on bottom, the change in the output on top, what is that? Show me you know something about math. The change in the output over the change in the input, what is that? One word, 5 letters. Well, at least it's one word and 5 letters. Shall I give you the first letter?
Yes.
S.
5 letter?
Just math. Ends in an E. You started studying it in middle school. You did it a lot. Slope. It is slope.
Wow. Pretty hard.
It's the change in the output over the change in the input. That's slope. So what we're really doing here is if the graph of f, which is the position function over time, you don't need to draw this if you don't want to, looks like this, then the average rate of change between those 2 points is simply the slope that connects them, of the line that connects them. It's a pretty cool idea. It's just the change in the function, delta f, over delta t. That slope gives you the average rate of change. Okay? Average rate of change, we're going to come back to it several times. What we're eventually interested in, though, is instantaneous rate of change. So, let's move on. So, a bowling ball is dropped from the top of an 800-foot tall building. If you've never watched any videos with things like this, they're freaking hilarious. You should do it. Okay, there's all kinds of different ones. Ones where they try to drop them on trampolines.
Oh, I watch stuff like that when they drop it like from a dam. I like watching that.
Yes, the one where they and it as it was going down, it didn't drop straight down. It was like moving from side to side and stuff.
Yeah, I like watching those videos.
Right. So
I'll show you physics for it.
the question is, what is its average speed during the first 3 seconds of fall? Okay. Well, you need to know the position function for this. So the distance traveled in t seconds is 16 t squared feet. And you may recognize that from physics, where acceleration due to gravity is negative 32 feet per second per second. You can, from that, get this equation. We will actually talk about, some of those motion equations from physics. We're going to actually talk about the math behind those. Okay? So, the average, the average speed, which is an average rate of change in position, is going to be equal to the 16 times 3 squared minus 16 times 0 squared, because we're going from 0 seconds to 3 seconds, over 3 minus 0. By the way, you could do it the other way around as long as you switched both of them, the numerator and the denominator. So let's see. That's 9 times 16, which is 144. Minus 0 over 3. Let's see, that's 48 feet per second. That's fairly straightforward. As long as you know the equation for the motion, you can figure out the average rate of change in the position, or the average speed. So one other thing we're interested in that's a little bit different than that is the instantaneous speed. So a body's instantaneous speed is the speed of the moving object at any given instant of time. And that causes a problem with our previous formula, because if you're doing it at an instant in time, do you have two different points? You only have 1 point. And if you only have 1 point, pretty difficult to get the slope. Right? You need 2 points to get the slope. So what are we going to do? Well, let's find the speed of the ball in the previous example at the instant t equals 2 seconds, both numerically and algebraically. Okay? And we're actually going to estimate it numerically. So how are we going to do that? Well, if we did the interval from 0 to 2, that's an interval of time, right? We want it at an instant in time. Now, we don't have a formula for that, at least not yet, but what could we do that would give us a better estimate of what was happening at that instant in time rather than that long interval of time? Divide what by 2?
Do a shorter interval?
Do a shorter interval. In fact, what if we made it a really short interval?
1.9.
Okay, 1.9 to 2. We could do that. We could also, is that better than 2 to 2.1? You could do both and then do what with those? You could do both and average them. There are lots of different ways you could estimate the instantaneous rate of change. Okay, now if you go from, the nice thing about going from 1.9 to 2.1, yes, it's a longer interval, but it's not one-sided. Right? It's not all the time before or all the time just after. It includes the time at. So I tend to do that when I'm estimating. So let's take a look at that. So the instantaneous speed should be approximately equal to 16 times 2.1 squared minus 16 times 1.9 squared over 2.1 minus 1.9. I need to just put my calculator up here. I think it's back here on my desk. So let's see. If I do 16 times 2.1 squared, you should be doing this too instead of just waiting for me to do it. Divided by 16 times 1.9 squared, divided by 0.2. Comes out to be 64 feet per second. Okay, came out to be a pretty nice number. And actually, as it turns out, because of the way this particular function works, not only did it come out to be a nice number, that's actually the exact number. And it seems odd that it should be the exact number. And one way that I can sort of verify that it probably is the exact number at this point, Lance, you said make a smaller interval. What if I made the interval even smaller? What if I did 16 times 2.01 squared minus 16 times 1.99 squared over 2.01 minus 1.99. Everybody try that on your calculator.
I'm in the process of getting a new one.
Again?
Yeah.
How far along in this process are you? Because it's not a very long process.
I'm trying to find the cheapest TI-84 I can find. They're expensive.
Is any TI-84 mount ordered yet? Whoa, that's pretty wild.
What does this one end up being?
64.
It ends up being 64 also. Now, I will say, this is a very special function where that happens to work. In most cases, what's going to happen is as you make smaller intervals, you have slight adjustments in your answer, and your answer becomes closer to the correct answer. It just happens on this one that it came out to be the exact answer for reasons that we won't discuss for a while. Okay? All right. Well, let's do this algebraically. You're like, how in the world are we going to do this algebraically?
Algebra.
Well, what we really want, remember that our formula, you don't need to write this down, but the average rate of change was f of t plus h minus f of t over t plus h minus t, right? Okay. We know the function. We know the time. We want t to be 2, right? What do we want h to be?
It was 800, wasn't it?
No.
No, oh, that's from the previous answer.
H is the change in time. What do we want the change in time to be?
0.
0, but if we substitute in 0, we're going to get 0 in the numerator and 0 in the denominator.
That's bad.
That's not very helpful, is it?
No.
First of all, because you can't divide by 0. And secondly, because, well, if you're substituting in, 0 divided by 0, is that 1? Because a number divided by itself is 1. Is it undefined because you can't divide by 0? Is it 0 because 0 over anything is 0? We'll talk more about this later, but this is called an indeterminate form. 0 divided by 0, as a limiting idea, it can exist. As a value, it doesn't. Okay? So what we're going to do here is go, okay, what if I made h really small? In other words, what if I took the limit as h went to 0 of f of, I'm going to go ahead and put in 2 plus h, minus f at 2 over 2 plus h minus 2. Okay, now my formula is 16t squared, right? So this is going to be equal to the limit. You never stop writing the limit until you have evaluated the limit of 16 times 2 plus h quantity squared minus 16 times 2 squared all over 2 plus h minus 2 is just going to be h. Something lovely is going to happen here. Let's look at what. So that's going to be the limit as h goes to 0 of, let's see, 2 plus h squared is 4 plus 4h plus h squared minus 16 times 4 is 64 all over h. Distributing the 16, we have the limit as h goes to 0 of 64 plus 4h plus h squared minus 64 all over h. What can I do to simplify the numerator?
Get rid of 64.
Exactly. Get rid of the 64. You're like, well, I'm not sure that that's all that helpful, but so this would be 4h. Oh, sorry, I didn't distribute the 16 there. My fault. This should be 64h because it's 16 times 4, and this should be 16h squared. I said distribute, and then I didn't do it. I guess I'll go straight to mathematics hell. Which is where you have to teach people who can't add how to do calculus.
Is that different from geometry?
Yeah, geometry hell's a different place altogether. So this is 64h plus 16h squared divided by h.
You can get rid of the h.
Yeah, you can divide out the h. Now, here's the deal. As a function, this function and the divided out by h function are not the same because you have eliminated the fact that there's a 0 on bottom. But as a limit, they are the same. Because a limit, we don't care what happens at a particular point. We care what happens as you get close to that point. So this is equal to the limit as h goes to 0 of 64 plus 16h. Oh, and isn't that nice? We can just substitute in 0, and that's 64 feet per second. It's a little bit of algebraic maneuvering, and bingo, this pops out. All right, let's move on. So, limit properties. You probably used these ideas when you did limits in your pre-calc class, but probably never formalized them. So, let's look at them. The limit as x approaches c of k is k, where k is some constant. Notice there's no x in the parentheses, so it doesn't matter what x does. That's a constant. It's always equal to k. Just a reminder here, these limits, think of them as the output of the function. So the limit as x approaches c of x is c. That's pretty self-evident. When x gets close to c, what does x get close to? C. Okay. The next one, you can add or subtract two functions' limits. The limit as x approaches c of f of x plus g of x is whatever f of x goes to plus whatever g of x goes to. Same for subtraction. Also true for multiplication. That's pretty nice that I could multiply those answers together. For number 6 here, instead of multiplying two functions together, I'm multiplying times a constant. Well, I can just figure out what does the original function go to and multiply the constant by that. If you think about graphically, if you multiply a quadratic, say, by 5, all the function values just get 5 times bigger, right? Same thing here. We can divide, but only under certain circumstances. We can divide provided that the denominator's limit is not 0. If it is, now we're dividing by 0, which again is pretty much the only thing in math that is permanently forbidden. There's all kinds of things in math that you get told are not legal, and then you find out later you can. Like when you were very young, you may have tried to take 7 from 3, and some well-meaning elementary teacher said you can't take a bigger number from a smaller number. And then later on you found out, oh yeah, you can. There's this whole negative number thing. Or at some point you were told, yeah, you can't take the square root of a negative number. It doesn't make any sense. And then you learned about imaginary numbers, and you're like, oh yeah, I really can. Division by 0, I don't know of any place where that eventually becomes, oh yeah, we can do that. It's the one thing that is constant, it's like, don't eat of the tree in the midst of the garden. You can have everything else. It's a little bit like that. Okay? It's the one thing that's sort of permanently forbidden. And we can also raise it to a power, as long as that power is some constant. So, one of the other nice things, for any polynomial functions, f of x and g of x, if we're just doing a polynomial, we can simply substitute the value into the polynomial to find the limit. Why is it that works so nicely? Because polynomials, when you're drawing them, do you ever pick up your pencil to draw them? For a polynomial? No, you never do. And so whatever point you're approaching is where you are. Likewise, for rational functions, provided the denominator is not 0, which is where you have things like vertical asymptotes and removable discontinuities or holes in the graph, provided that doesn't happen, wherever you are in your drawing is the limit at that point. You can just substitute. So, let's find some limits. So for example, the limit as x approaches 4 of x squared times 3 minus x. And let's use big boy words now, shall we?
Can you substitute x?
Thank you. Let's substitute 4 for x.
I don't know. I kind of like saying plug in. Should
Plug and chug is one of my favorite phrases, but when you're saying what you're doing, substitute.
Oil.
Nasty.
So I hate FOIL for two reasons now. One is that it's a crutch for the distributive property,
Bad students.
right? The second reason is because of the way my hearing works now. I'm deaf in my left ear, but I have a constant ringing in it, and loud noises and certain other sounds make it worse. If you crumple aluminum foil in my presence, there's every chance I will go for your throat. Just saying. There are certain sounds that set it off, and it's like, it's not painful. It feels like it should be. If ever any of you have ever gotten your bell rung or something, you're like, it's like, this much volume should be painful, but it's not. Thank goodness. All right. Anyway, back to this. Here, we want the limit as x approaches 2 of x plus 3 over x minus 2. Well, if we do that and we just substitute in directly, we get 5 over 0, right?
Bad.
That's bad. And the question becomes, does this limit exist or not? It turns out that this limit does not exist. So the way that we write this is DNE.
Sounds a lot like DNA.
Like a do not resuscitate? Wow. That got dark in a hurry. But just because you have 0 in the denominator does not mean that the limit doesn't exist. Take, for example, this problem. If we substitute in -1 for all of the x's, we get 1 minus 5 is -4 plus 4 is 0. And in the denominator, we also get 0. When you get 0 divided by 0, that is indeterminate.
Why is it not 1?
Why isn't it 0?
0 doesn't have a value, so 0 can't go to 0.
And yeah, there are 3 competing rules here, right? 0 divided by a number, supposed to be 0. A number divided by itself, supposed to be 1. A number divided by 0 is undefined. Which one do we say it is?
All 3.
What we're going to do is we're going to determine this limit by using a little bit of algebra. Not a lot. Some basic things. You need to be able to factor.
Yeah. I love factoring.
If you aren't good at factoring, this may be painful for you. So factoring the numerator, that's x plus 4 over times x plus 1 over x squared minus 1.
X minus 1 squared. Oh, x plus 1.
Yeah, x plus 1, x minus 1.
You can cross out the x plus 1.
Yes, because it's a limit, you can. If it's not a limit, you cannot. Because right now, this is, if you just look at the function, this function is undefined because it has 0 in the denominator. If you cancel out, I prefer to say divide out, but if you divide out those x plus 1s, now it is defined and you have changed the function. But as a limit, that is perfectly legal because we don't care what happens at -1. We just care what happens near -1 as we approach -1. So we will divide those out, substitute in. Now we have -1 plus 4 is 3 over -1 minus 1 is -2. So this is -3/2 or -1.5, whatever you like. What would actually happen if you were to graph this function is that at the point -1, there would be
There's a hole.
a hole. The y value would be -1.5 at that hole. Okay, very good. By the way, I mentioned, you got to be able to factor. One of the things that calculus does to you is pretty much all of your algebra and some of your pre-cal. The reason that it's taught is so you can do calculus. And so anything that you're weak at, calculus will find it out and it will point it out to you painfully. Okay? It's not the calculus itself. The new things that we learn, a lot of them are not all that hard. But you got to be able to do everything before well. Okay? All right. Let's look at this last one. The limit as x goes to 0 of sine of x plus 4x over x. And there's a note here. This is a limit that I'll show you why it works in just a second. But for now, you just need to put that in your memory. That needs to be something you have memorized. The limit as x goes to 0 of sine of x over x is equal to 1. By the way, that also means the limit as x goes to 0 of x over sine of x is 1. You're just taking the reciprocal of both. Okay? Well, how does that help me with this? Well, what I need to do is rewrite this original limit. I'm going to rewrite this as the limit as x goes to 0 of sine of x over x plus 4x over x. That's algebraically legal because I'm dividing both parts of the numerator by x. This first part, I've been given what that is.
Yeah.
What can I do with this second part?
Get rid of the x. Or divide out the x.
Yeah, divide out the x's. Again, legal because this is a limit. So this is going to be 1 plus 4 is 5. Okay? Let me real quickly show you that sine of x over x it goes to 1 as x goes to 0. All right, this is the graph of x over sine of x. You could do sine of x over x. It would be a different looking graph, but the same thing would happen. Notice when I try to trace this to x equals 0, the function doesn't exist because the denominator is equal to 0. Your calculator used to not do this. They used to fill stuff in like that, and I was like, that's horrible. You shouldn't fill those in. But if I move this ever so slightly to the right, notice the y value is very close to 1. We move it to the other side. My x is still pretty close to 0. My y value is very close to 1. Okay, so this is one of the ways that we'll look at limits. Some will be to go, okay, I can look at the graph and go, yeah, there's a hole there, but I can figure out the coordinates of the hole. Okay, any questions about any of that? I think that's it. Yep.
No questions.
All right. Your assignment will be in the book and it'll be due tomorrow. Tomorrow I will not be here. I think I told you guys, I have jury duty.
Yeah, my phone with that.
You,
Can you tell us the juicy details?
yeah. I'm going to be on the Deshaun Watson grand jury.
One of his 50 cases.
So you guys will report to the NAC.
Sweet.
And
Do you have work to do in the night, or is it just
yes, so what's going to happen?